All right, so today we're looking at lesson 46. We're looking at circular motion, part 2. We've already looked a little bit at circular motion this year, so we're going to focus on it a little bit more. So hopefully you'll understand circular motion after this lesson. If you have an object that's moving along a circular path at a constant speed, the direction of the linear velocity vector is always going to be changing. And so we have a constant velocity as we move around our circle. We have a constant speed as we're moving along our circle. It's moving in a circular path and your speed is constant. But the vector velocity, it's always going to be changing because it's changing direction. Remember that for your velocity to be constant, you would have to have the same speed and the same direction. But since the direction is changing, that means that your velocity is actually changing. So a change in magnitude or direction of your velocity is actually called acceleration. And if you have an object that is going to move along a circular path at a constant speed, the object is going to always be subject to a linear acceleration that's directed toward the center of the circle, and it's always going to be perpendicular to the instantaneous linear velocity. So if it's moving along a circular path at a constant speed, it's not a constant velocity because the velocity is changing. If it's moving at a constant speed, your speedometer on your car would be at the same number the whole time. Then your object is going to be subject to a linear acceleration, and that acceleration is directed towards the center of the circle. The acceleration that's towards the center of the circle is called centripetal acceleration. So that's going to be called your centripetal acceleration. And they note centripetal acceleration with the A sub c right here. So that A sub c is how they note that your acceleration is centripetal acceleration. That A sub c. The magnitude of the acceleration is always going to equal the square of the magnitude of the linear velocity divided by the radius of the circle. And so that would be the square of the velocity divided by the radius of the circle. And they have a proof later in the lesson if you want to look at it on page 312. It proves that formula. You don't have to look at it unless you're just, really curious about it. We can also write our centripetal acceleration as r, and then remember that this is the angular speed. That's our formula for the angular speed. And you remember that v equals r omega. And then we can say, instead of v squared, we can write r omega squared. And so we would have r squared and then omega squared over r, which r squared over r reduces to r, and then we have our omega squared. So that's how you can change this formula into the one on the left if you want to. But those are the two forms for your centripetal acceleration. So let's look at an example. We have a car that drives at a constant speed of 10 meters per second around a circular track whose radius is 40 meters. We want to find the centripetal acceleration of the car. And then if they drive at the same speed around another track whose radius is 70 meters, we want to find the centripetal acceleration. So we're going to use the formula that was on the right. We're going to use this formula here, v squared over r. The v is our 10. That was the speed that we were going. So we're going to say 10 squared. And then our radius is 40 meters. And so 10 squared is 100 divided by 40. You're going to have 2.5 meters per second. So that would be, I'm sorry, meters per second squared, because we're dealing with acceleration. So that would be your centripetal acceleration about a 40-meter track. For the other one, we would still have v squared over r, but our v stays the same and our r changes to 70. And so 100 divided by 70 with 2 sig figs is 1.4 meters per second squared. So do you see how this acceleration, 2.5, is bigger than this acceleration, 1.4? The acceleration is going to be larger for the track with the smaller radius because the car is going to have to change directions more quickly. If you think about running to a tree, running around it, and coming back, is it hard to stay really, really close to the tree? Or is it possibly a little bit easier to make a little bit wider loop and come around? It's a lot harder to stay in that little bitty turn. And so that's why our acceleration is bigger for the circle that has a smaller radius, because it's a lot harder to turn more quickly at the same speed. And so I don't even know if you've realized that you've done that before, but when you run somewhere and then you turn around and run back, you're usually going to make a little bit wider loop unless you slow down or you stop and turn around. So that's the first example. So we're going to look at Newton's first and second laws for that. You remember that was the F equals ma. F equals ma was Newton's second law. We can write these two expressions here on the board for the centripetal force. So if we replace the A with the A sub C that we have up here, instead of having A, we can say either r omega squared or v squared over r instead of your A in this formula here. You can come up with these two formulas. And so that is the expression for the force that you would have to keep an object of a particular mass m moving in a circle whose radius is r. Okay, so let's look at an example. We have a small cube whose mass is 0.4 kilograms, revolves in a circular orbit on a frictionless table about a pin as shown. The speed is constant at 2.4 meters per second, and the length of the string is 0.3 meters. What is the tension in the string? So we need to figure out what is the force. That's the same thing as the tension. The tension is the force on this one. So our force, our tension equals our force, and we can use one of the two equations from the last slide. We're going to use m and then v squared over r because we don't have the angular speed. We have the linear speed because it's meters per second. So our mass is 0.4. Our linear speed is 2.4, and then you square that, and then the radius is 0.3. And so if you multiply those and then divide by 0.3, you get 7.68. And so that means we have two significant digits here. We had 3 here, and we have 3 here, but since we only have 2 at this 2.4, this gets rounded to 7.7, and force is going to be newtons. Okay, so that's how you work that example. Looking at the next example, the tensile strength of a string is 89 newtons. One end of a 1 meter piece of string is tied to a 4.54 kilogram toy car. The other end of the string is attached to a ring that slipped over a pole. Neglect friction and determine the angular speed in revolutions per minute that the car can drive without breaking the string. So we know that our tension is going this direction. So the tension has to equal our centripetal force. And on this one, we want to determine the angular speed. Angular speed, that is the omega, so we're going to have mr omega squared. So our tension, they told us the tension, the strength of the string is 89. And we don't want to break the string, so we can go no higher than 89 for our strength. Okay, our mass is 4.54. Our radius is basically going to be just the length of the string. Because if we make a circle, oh, that's a terrible circle. The radius is going to be this length here, which is the length of the string, which is a 1. And then we're going to solve for our omega. And so if you solve that, you should get 4.43. And the units on this is going to be radian per second, because we're dealing with newtons. Our part here, omega, is going to come out in radians per second, but we need to find it in revolutions per minute. Revolutions per minute. So remember that 2 pi radians is 1 revolution, and then to change second to minute, 60 seconds is 1 minute. And so if you multiply that, you get 42.3 revolutions per minute, which would go to just 42, because we have 2 sig figs, 2 sig figs, and then we have 3 sig figs. So 42 revolutions per minute. Okay. If that's not what you got when you plug this into the calculator, make sure that you do 4.43 and then times 60 and divide by parentheses around your 2 pi. You've got to put the parentheses, otherwise it's going to divide by 2 and then multiply by pi. Okay? So looking at one more example, we have a child that swings a 1.2 kilogram ball along a circular path with a radius of 0.62 meters. The instantaneous linear speed of the mass is 2 meters per second. Find the tension in the string. So on this, our tension is going this direction towards the center, and then our mass times the gravity, the weight of the ball, is coming down. So first we need to figure out what our centrifugal force is. And we're going to use mv squared over r. So our mass is 1.2, our v is 2, and then our r is 0.62. So if you multiply those, you get 7.742. That's not the tension in the string because it's at an angle here. So since it's not straight down, straight out, like it's not completely horizontal, that's not going to be the tension in the string. We now need to find the mass times the gravity, the weight. So the weight is 1.2 times 9.81. And so that gives us 11.77. So then the tension is the horizontal component and the vertical component. We have a horizontal component that is the F sub C. This is your F sub C because that's the force that's perpendicular to the center of the circle. And then your mass times your gravity is acting down. And so your weight is the vertical part. And so the tension has both a horizontal and a vertical component. And so to find the tension, we've got a right triangle here. and so we just use Pythagorean theorem to get our tension. So the tension is the square root of the weight squared plus the centripetal force squared. And so plug those numbers into your calculator, and you should get 14.1 newtons. Okay? So the tension isn't just the centripetal force on this one, because it's not going horizontally. It's at an angle, and so the weight is also pulling more, and it makes the tension greater than just having the centripetal force. Okay? So your homework is 1 through 20, and then also number 1 through 5 on the curveball questions. So make sure that you do those tonight so that we can go over any questions that you have tomorrow.